This is my trigonometry course. Today we're going to show that equations are true using the identities that we learned in the previous class. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. So if you don't have a picture on your phone of these identities at the left, go ahead and take a picture or get a screenshot. You're going to need these right in front of you. We learned these identities in the previous class, but if you don't have those memorized, make sure that you have those basic identities right in front of you. In the previous class, we simplified expressions using those identities. Today we're going to do something similar, but what's different with today's lesson is we have equations, and we're going to simplify expressions in those equations in order to show that the equations are true. So it's very similar to what we did in the previous class. And it says here, prove that each equation is true by converting the left side to the right. So I'm going to make things easy for you. Just tell you to start on the left side. So let's demonstrate what we are going to do here. With this first problem, we have an equation, and we're going to show that that equation is true by taking one side. It's always going to be the left side with these problems. The reason I'm telling you which side to start with is because it introduces some complications when you have to determine which side to start with, and we don't want to have to deal with that when you learn how to do these problems. So we're going to always start with the left side. And we're just going to work on the left side and ignore the right side and show that this expression is equal to sine squared alpha. So there are three purposes for this class today. One is to help you to memorize the identities that we learned in the previous class. It's not enough to just be familiar with those identities, you have to have them memorized. And the second purpose for this class is to show you how to structure a proof, how to show it on paper. And the third reason is to do some more rigorous algebra. In the previous class, the algebra that we did really was pretty basic, but now we're going to get into some more difficult expressions. We're going to start with a ratio identity. Tangent alpha is equal to sine alpha over cosine alpha. We learned that in the previous class. And why do we care about that? Well, it's going to change the form of the overall expression on the left side of the equation. We have a cosine that's going to cancel out because we have a cosine on the bottom there. And we're just going to multiply these signs to get sine squared alpha. And you can see that we proved it. Now, one thing that I want you to do is to carry down this equal sign, not really because we need it to show that it's equal to anything, because we don't assume that this expression is equal to sine squared. That's what we're trying to prove. But I want you to carry that equal sign, or continue that symbol as we go into each step, because it demonstrates that we're on the left side of the equation. That's really the only reason that we're using the equal sign, to show that we're only working on the left side of the equation. So now you can see that we're done. We proved that the equation is true, and we can put a big check mark. That means we did it. We proved the equation is true. Okay, let's try another one of these problems. Now let's use a reciprocal identity. Now, there's multiple ways that you can solve or complete these problems. So if you think of a different way and you want to try it, that's fine. But I used a reciprocal identity. And again, we have a tangent omega in the denominator of the fraction. So it cancels the other tangent omega out, and we're left with secant omega. Now, we still have not proven that this side is equal to this side, we have to do one more thing. We have to use another reciprocal identity, and we get 1 over cosine omega, and now we've done it. We showed that the left side of the equation is equal to the right side, and therefore the equation is true. So we can put a big check mark. Okay, let's try a couple more of these before you try one on your own. We're starting with very easy problems. So you know, well, let's put these expressions together. Let's put sine squared beta and cosine squared beta next to each other. You don't really have to show this step here. But I just want you to be aware that this expression exists on the left side of the equation, and obviously you know that that is equal to 1. So again, we have another problem where we proved the equation is true pretty easily. And again, the only reason we're writing these equal signs is to show that we're on the left side of the equation. That's really the only reason that we're rewriting the equal sign. Okay, let's try number 4. You know that secant squared is the same thing as tangent squared plus 1. So I used a Pythagorean identity. And 7 plus 1 is 8. And there you go. We're done. So we're starting off with pretty easy problems in order to demonstrate how to prove these equations. And another name for what we're doing right now is proving identities. Again, they like to use that fancy word identities in the math curriculum. So I want you to take a picture of the first 4 equations that we did, and that'll give you an opportunity to take a picture of the basic identities if you haven't already done that. So now it's time for you to try. Go ahead and attempt number 5, and when you come back, we'll do it together. Okay, we're back. So cotangent theta is cosine theta over sine theta. How do I know that? Well, that's one of the ratio identities that we learned in the previous class. And again, if you don't have these in front of you, then you're going to go precisely nowhere in this class. So you need these right in front of you. If you have not taken a picture of those, or if you don't have them memorized, you should have those right in front of you. So cotangent becomes cosine theta over sine theta, and as you might expect, those sine thetas cancel out, and cosine theta times cosine theta is cosine squared theta. So we proved that this side of the equation is equal to that side. So we can put a big check mark, meaning that we proved it. Okay, go ahead and try number 6, and when you come back, we'll do it together. All right, we're back. So I'm going to convert cosecant A to 1 over sine A. And those sine A's cancel out, and I'm left with tangent A. And again, notice that we're not doing anything to the right side of the equation. We're just trying to make the left side look like the right side of the equation. So tangent A is 1 over cotangent A. I used a reciprocal identity, and I used a reciprocal identity again, and we proved that the equation is true because we showed that the left side is equal to the right side. So if you got that one right, excellent. Try number 7. When you come back, we'll do it together. Okay, we're back. So again, we want to group the sine squared beta and the cosine squared beta together Whoops, those are not betas, those are b's. Sorry. B's and betas look similar, but they're not quite the same. Okay, so we grouped our sine squared and our cosine squared, and you know what that means. That's a Pythagorean identity. So we have 1 minus 2 sine b, and we did it. We proved that the equation is true. So we can put a big check mark. So if you got that right, excellent. Try number 8, and when you come back, we'll do it together. All right, we're back. So cosecant squared is equal to 1 plus cotangent squared. How do I know that? Well, that's one of our Pythagorean identities. And 1 plus 2 is 3. And there you go. We proved that the equation is true. So we got that right. Excellent. Now, again, important things to note as you're doing this is we're only working on the left side of the equation. We're not touching the right side of the equation. We're also not assuming that the equation is true. A lot of students will try to do something to both sides of the equation. You can't do that. You cannot assume that the equation is true. You're only working on the left side of the equation. I know that's kind of strange, but we haven't done these problems in the past, so this is strange. Anything that we do that is new is going to feel strange, and that's what mathematics is all about. You're learning fluency in a language. So whenever you're learning fluency in a language, it always feels weird when you first attempt to do that. So now we're going to do problems that require the distributive property, also called the distribution rule, however you want to word that. We have a cosine function that is multiplied by the sum of two other functions. And remember, we're always going to start on the left side of the equation. I gave you those directions at the beginning of the problem set. So what we're going to do, when you multiply some expression by a sum or a difference, you take that expression, multiply it into the first term, and then you add that product to the product of that expression and the second term. And if there's a third, or fourth, or fifth, or sixth, you just keep going. So what this means is we have cosine theta times cosecant theta. So we multiplied cosine theta times cosecant theta. Then we're going to multiply cosine theta times tangent theta. And if you can, try to write the equal sign straight down. You don't really have to, because sometimes, as you can see, it's not easy to do that, but you want to try to keep the equal sign straight under the equal sign in the previous step. It's not that important, but it's preferred that way. So we are now going to use excuse me, we're going to use a reciprocal identity. We're going to change that cosecant to 1 over sine, and we're going to change the tangent theta to sine theta over cosine theta. So when we multiply these terms here, we get cosine theta over sine theta. And when we multiply these terms, you can see that the cosine thetas cancel out. And this is a ratio identity. Cosine theta over sine theta is cotangent theta. So there you go. and we can put a check mark. Now let's try one more of these before you try one on your own. We're going to use distribution. Again, we're always working on the left side of the equation. So sine squared alpha times 1 is sine squared alpha. Sine squared alpha times cotangent squared alpha. So we use the distribution property, and now we're going to change cotangent squared alpha to cosine squared alpha over sine squared alpha. And you can see that the sine squared alphas cancel out, and we're left with sine squared alpha minus cosine squared alpha. So that was a ratio identity. And now we're going to use a reciprocal identity for the last step. We want 1 over cosecant squared, so we're going to change the sine squared alpha to 1 over cosecant squared. And there you go. So we proved it. We proved that the left side of the equation is equal to the right side of the equation. So go ahead and take pictures of number 9 and number 10. And you're going to use 9 and 10 to help you do number 11. So go ahead and try number 11. And when you come back, we'll do it together. Okay, we're back. We're going to use the distributive property. And secant omega is 1 over cosine omega. And cosecant omega is 1 over sine omega. So I used 2 reciprocal identities. Then I'm going to multiply these, and I get sine omega over cosine omega plus, well, these sines cancel out. If you want, you can write sine omega over sine omega, but it's really not necessary. You can just write 1. And sine omega over cosine omega is tangent omega. That's a ratio identity. And there we go. Okay, go ahead and try number 12. And when you come back, we'll do it together. Okay, we're back. So we're going to use distribution. Cosine squared y times 1 is equal to cosine squared y. And cosine squared y times tangent squared y. Whoops, that's a cosine squared y. And then we're going to use a ratio identity. Tangent squared y is equal to sine squared y over cosine squared y. And notice that the cosines cancel out, the cosine squared y's. So we have cosine squared y minus sine squared y. And we need to change cosine squared to 1 over secant squared. And we're going to use a reciprocal identity for that. And so there you go. So we proved it. Again, we proved that the equation is true, by showing that the left side is the same as the right side. So if you got that one right, good job. Okay, so let's try some more problems here. In the previous class, the algebra was really not that difficult. It was pretty basic algebra. We did use FOIL, which is a more complicated concept, but we didn't really get into the more rigorous algebra. Well, now we're going to get into some more rigorous algebra. That's one of the purposes of this class. You might think, well, aren't we just doing the same thing over and over again? Well, no, we're going to review many things, but we're also going to get into some more rigorous algebra. And this is a perfect example of that. We're going to do something called fraction decomposition, and all that means is that you're going to take a fraction and break it into multiple fractions. For example, you might have 3/4. You could break that into 1/4 plus 2/4, right? That's legal, right? We don't really do that very often, right? But we do. We can do that. There's nothing wrong with it. Well, in these problems, we're going to have to use fraction decomposition. So I'm going to break that fraction on the left side of the equation into cosine squared beta over sine beta times cosine beta. Okay. How is that possible? How can we do that? Well, in order to understand why that works, go in the opposite direction. Take this expression here and ask yourself, how can we go from here to here? How can we do that? Well, we have a common denominator. You see these denominators here. Remember, if you are adding or subtracting fractions, you need a common denominator. Well, we have that. So we can combine the fractions and go ahead and add or subtract the numerators. In this case, we're going to subtract the numerators. So that's what it means to decompose fractions. Now, why did we do that? Well, because we have cosine squared beta over cosine beta. That's exponent rule number 2. For example, if you had x squared over x, we could use exponent rule number 6 to say that that's x to the first power. Then use exponent rule 2 to say we just subtract the powers, so we get x to the 2 minus 1, which is just x. So that's what we're doing here. Cosine squared divided by cosine is just cosine. And if you're having trouble understanding why that is, what you can do is you can factor the numerator. All I did is just change the form of cosine squared beta to cosine beta times cosine beta, and you can see that two of these cosine betas cancel out. They're just factors that cancel out. Now, you don't have to show that step, but if it helps you to understand, you can do that. So cosine squared beta over cosine beta is just cosine beta. There's more cosines in the numerator, so that's why the leftover cosine is in the numerator. And of course, we do the same thing with the other expression. And of course, we have cotangent beta minus tangent beta, and that's what we're trying to do. We used a ratio, or both ratio identities we used, and we proved that the equation is true. Okay, let's try another one of these problems. Again, we're going to use fraction decomposition. So we have a common denominator here. If I went backwards, I would just subtract the numerators and combine the fractions, but we went in the opposite direction. So now we have sine to the fourth power over sine to the second power. 4 minus 2 is 2, so we're left with 2 sines in the numerator. And cosine to the fourth divided by cosine squared is cosine squared. So again, we're left with 2 cosines in the numerator, and you can see that this is kind of exactly the same problem that we did previously. Sine squared over cosine squared is tangent squared. And we have cotangent squared, so it's pretty much the same problem that we did before. So we proved that the equation is true. Alright, so I want you to get a picture of number 13 and 14. You can use that as you attempt number 15. Try number 15. You're going to use fraction decomposition. You're going to break the fraction into 2 parts. And when you come back, we'll do it together. Okay, we're back. So if we break that fraction into 2 parts, we have cosecant A over cosecant A times cosine A. And as you can see, these cosine A's, they cancel out, and these, the cosecant A's cancel out, and at the right, the cosine A's cancel out, and we're left with 1 over cosine A minus 1 over cosecant A. The difference with these problems is that they disappeared completely. So we have cosecant to the first power divided by cosecant to the first power. Subtract the powers, you get cosecant to the 0 power, and anything raised to the 0 power is 1. That's one way to think about it, but that's a lot of complications you don't really need to consider. If you're dividing something by itself, it's going to be equal to 1, as long as that thing you're dividing is not 0. So now we're going to use reciprocal identities, and we get secant A minus sine A, and that's what we were trying to prove, that the expression at the left was equal to the expression at the right. So now we can put a check mark, and you're done. So if you got that right, excellent. If you made a mistake, or if you weren't sure how to do that, that's fine. Your mind is slowly starting to become familiar with the procedures here. Try number 16. When you come back, we'll do it together. Okay, we're back. So again, we're going to use fraction decomposition. So we're going to break it up into this fraction and this fraction, and of course we're going to use a ratio identity here, so we get cotangent squared b minus 1, and as you can see, that was pretty easy. So if we got that one right, excellent. Okay, so now we're going to use factorization to do some of these problems. Let's review the basic types of factoring. There's many types of factoring, but in algebra, the major forms that we need to consider are extracting the greatest common factor. You could also describe that as pulling out a greatest common monomial, or a GCF. And there's factoring quadratic expressions. That's expressions where you have a variable squared, a variable that's not squared, raised to the first power, that is, and you have a number with no variable. That's a quadratic expression. And then you have the difference of two squares. You have two squares, and you're subtracting them, so we say the difference of two squares. And this is a square because 6 squared is 36. This is a square because 7 squared is 49. And this is a square, obviously, because x squared is a square. So let's do some quick review here. This is all review of things that you've learned in previous classes, so we're just kind of jumpstart your mind if you haven't seen this in a while. So we're going to factor, we're going to pull out a GCF. We're going to ask, what is the biggest factor that's common to all of these numbers? The biggest factor that is present in all of these numbers. If you said 9, then you're correct. 9 goes into all those numbers. That's another way of describing it. 9 goes into them, meaning it divides. Now we're going to ask, what is the greatest common factor in terms of x's for all these terms? In other words, what is the greatest number of x's that's common to all three of the terms? Well, this has 2 x's, and these other terms have 2 x's also. You can't say 3 x's because this term doesn't have 3 x's. So the greatest common factor in terms of the x's is x squared. The rest of the problem is easy. We just ask 9x squared times what is equal to 27x to the fourth? 9x squared times what is equal to 27x to the fourth? And if you said 3x squared, you're correct. All right, now 9x squared times what is equal to 18x squared? If you said 2, you're correct. 9x squared times what is equal to negative 54x cubed? If you said negative 6x, you're correct. So that is the factorization of this expression over here. So that's pulling out a greatest common factor. It's always good to go back and check, make sure we did everything correctly, because there's a lot of computations that we did. Everything looks correct, so now I'd like you to try example 2, and when you come back we'll do it together. Okay, we're back. Alright, what is the greatest factor of all these numbers, or the greatest factor that's common to all the numbers? What is the greatest factor that's common to all the numbers? And the answer is 4. In terms of y, what is the greatest common factor of all the y's? What is the greatest number of y's that is common to all those? And that is y cubed. And so now we ask 4y cubed times what is equal to 8y to the 10th? And that is 2y to the 7th. 4y cubed times what is equal to 16y to the 4th? And that is 4y. And 4y cubed times what is equal to negative 4y cubed? And the answer is negative 1. So it's always good to go back and check to make sure we did each step correctly. So everything looks right. If you got that right, good job. So that was factoring a greatest common factor. That should all be review for you. Now we're going to factor quadratic expressions. So that's a quadratic. And this is something that you really should know pretty well by now. And we're just going to go through some quick review. So when you have a quadratic expression, oftentimes it can be factored to the product of binomials. Not always, but many times. And we simply ask, what are two numbers that multiply to 15 and add up to 8? We're looking for two numbers. And these two numbers, if you multiply them, you get 15. And if you add them, you get 8. So what are the two numbers? If you said 3 and 5, you're correct. So that is the factorization of that quadratic expression. So go ahead and try example 4. You want to ask yourself, we're looking for two numbers such that when you multiply them, you get -1, and if you add them, or excuse me, if you multiply them, you get -2, and if you add them, you get -1. So we need two numbers such that when you multiply them, you get -2, and you add them, you get -1. Try example 4. When you come back, we'll do it together. All right, we're back. So the answer is -2 and +1. And it doesn't matter if you put the -2 here or here. You can switch the numbers if you want, so you're going to get the same answer. Okay, try example 5. Again, you're going to write two sets of parentheses, and you're going to write an x and an x, and ask yourself, what are two numbers that multiply to 20 and add up to -9? Try example 5. When you come back, we'll do it together. All right, we're back. So the answer is -5 and -4. If you multiply these yellow numbers, you get +20. And if you add them, you get -9. If you multiply these numbers, you get -2. And if you add them, you get -1. If you multiply these two numbers, you get 15. If you add them, you get 8. So that's how we do this this type of problem. Now, we're not going to see many problems like this today because I don't want to bother you with those. But these are different because we have a coefficient on the x squared term. So this is a little bit more involved. And instead of x and x, we can have 2x and 2x, because 2x times 2x is 4x squared. Or we could have 4x and x. And we have to ask what two numbers multiply to -18, and it's going to be -3 and +6. It could be 1 times 18, it could be 2 times 9, it could be a lot of different things. But I'm just going to jump forward to the answer. And we check to see if this is true by using FOIL. But we're not going to do that right now because we need to get to the main part of this course. So before we go on to more problems, let's factor the difference of two squares. So we have to identify this expression as the difference of two squares. And one way to do that before we get started is to write 36 as 6 squared. We're subtracting two perfect squares. So it's the difference of two squares. So I'm going to factor into the product of two binomials and square root that number. We're square rooting both numbers. So what number times itself is x squared? That goes there. What number times itself is equal to 36? That goes there. This is just how you do these problems. We learned this in my beginning algebra course and also my intermediate algebra course, and you always write a negative sign and a plus sign when you're doing these problems. And it's important to understand that you have to have these methods of factorization memorized. This is not something that you try to figure out conceptually every time you do this. We don't have time for that. There are many things that you do in algebra and trigonometry and math analysis and calculus where you don't have time to sit down and conceptually figure it out. You're expected to know the rote math quickly. That's just, the way it works. That's why the prerequisites for math courses are enforced So now we have x squared and 49. So again, what number times itself is x squared? That goes there. What number times itself is 49? That goes there. So obviously 7 times 7 is 49, and we write a plus and a minus symbol. And it doesn't matter what side the plus and the minus are on because the binomials are the same. All that's different is the sign. Remember the commutative rule of multiplication. So now we have a similar problem, except we have a coefficient on x squared, but it's the same situation. What number times itself is equal to 9x squared? Well, that's just going to be 3x. What number times itself is equal to 25? Well, that's just 5. And write a plus and a minus symbol. Again, it doesn't matter which side, which binomial you write the plus or the minus on. So go ahead and try example 10, and when you come back, we'll do it together. Okay, we're back. What number times itself is equal to 4x squared? Well, that's 2x. What number times itself is equal to 81? Well, that's 9. And write a plus symbol and a minus symbol, and you're done. Again, it doesn't matter if you write your plus first or your minus first. So this is just basic factorization. And if you need more practice with this stuff, you can go to my beginning algebra course, and we also do a little bit of this in my intermediate algebra course. So now we're moving on to problems that require, of course, factorization. Notice that there's a cosecant A in both of these terms, so I'm going to factor that cosecant A out. And if I do that, I'm left with 1 plus cotangent squared A. So the purpose of this is to show you all the types of things that you can do to change the form of these expressions. And you can see that now we have a Pythagorean identity. 1 plus cotangent squared A is equal to cosecant squared A. And cosecant squared A times cosecant A is cosecant cubed A. And there you go. So we proved it. We used factorization. Now that was factoring out a greatest common factor, extracting the GCF. That was the first type of factoring, the most basic type of factoring. Well, now, immediately we're going into a quadratic expression, but this doesn't look like a quadratic expression. We're used to seeing something like x squared plus 7x plus 12, right? But now we have sine squared plus 7 sine x plus 12. So instead of x, we have sine x. Well, that's okay. It's going to work the same way. So we're going to factor to a product of two binomials, and we're going to ask what we're looking for two numbers such that when you multiply them you get 12, and when you add them you get 7. There are two numbers that multiply to 12, and if you add them up you get 7. So what are those numbers? Well, they are 3 and 4. So I factored the numerator. And why did I do that? Well, because we see that we have a common factor in the denominator and the numerator, which means that the fraction reduces. That's one way of describing it. The fraction reduces. And we're left with sine x plus 4, and that's exactly what we're trying to prove, that the left side of the equation is equal to the right side. So there you go. Alright, let's try one more of these problems. We did extracting a greatest common factor, and we factored a quadratic expression. Well, now we're going to factor the difference of two squares. So up here we have the difference of two squares. That doesn't look like the difference of two squares But if you rewrite it as 1 squared minus secant squared, you can see that it really is the difference of two squares. So we're going to factor to a product of binomials. Remember, the difference of two squares always factors the product of two binomials. And we're going to ask what number times itself is equal to 1 squared. What number times itself is equal to 1 squared? Well, that's just 1. And what number times itself is equal to secant squared? Well, that's just secant. And then, because it's the difference of two squares, we write a plus sign and a minus sign. And it doesn't matter which side. We can switch the order of the signs. It doesn't matter. So now you see that 1 minus secant theta and 1 minus secant theta is a factor of the numerator and the denominator, so we're left with 1 plus secant theta. And if we just go one step further and factor to, or not factor, but just use a reciprocal identity, we have our final expression, and there you go. So if you got that right, excellent. Okay, so now it's time for you to try. You're going to do a problem that's similar to this one up here. You're going to factor out a greatest common factor. Notice that both these terms have sign. You're going to factor out sign. So go ahead and try number 20, and when you come back, we'll do it together. Okay, we're back. Maybe I should make that a little bigger so we can see it better. So I'm going to factor out sine x, and we have 1 minus cosine squared x left over, and 1 is equal to sine squared x plus cosine squared x. And if you subtract the cosines, we're left with sine x times sine squared x. You don't really have to write the parentheses, but you can if you want to. And then we're left with sine cubed x. And there you go. So we proved it. If you got that one right, good job. That was an example of factoring the GCF, the greatest common factor. Number 21 is like 18, so you can use 18 to help you. Try number 21. When you come back, we'll do it together. Alright, we're back. So we're going to factor this quadratic to the product of two binomials. But instead of x, it's going to be cosine x, and we're going to ask, we're looking for two numbers that multiply to 9 and add to -6. The two numbers we're looking for, if you multiply them, you get 9, and if you add them, you get -6. So the answer is -3 and -3. And you can see that we have a common factor, and you can factor the expression on the left or the right, it doesn't matter, but one of them is going to remain. So we're left with cosine x minus 3. So if you got that right, good. Go ahead and try number 22. Number 19 will help you with number 22. And when you come back, we'll do it together. Okay, we're back. So this is the difference of two squares. If you write a square on the one, you can see it's a difference of two squares. So we're going to factor to a product of binomials. What What number times itself is cosecant squared theta? Well, that's cosecant theta. What number times itself is equal to 1? Well, that's 1. And then, of course, we write a plus symbol and a minus symbol. And then we're going to cancel these expressions, and we're left with cosecant theta minus 1. And we're almost done. We have to use a reciprocal identity. And there you go. All right, so if you got that one right, excellent. So those were examples where we had to factor. And now we're going to do a couple more examples. Here we have the difference of two squares again. So it's going to factor to the product of two binomials. What expression times itself is equal to sine squared theta? Well, that's just sine theta. What expression times itself is equal to cosine theta squared? Cosine squared theta. What expression times itself is equal to cosine squared theta? Well, that's just cosine theta. And then we write a plus and a minus symbol. How do I know to write a plus and a minus symbol? Because it's a difference of two squares. That's just how we factor the difference of two squares. So now we're going to cancel out. And we're left with sine theta minus cosine theta. All right. So I want you to try number 24. 24 is very similar to 23. When you come back, we'll do it together. Okay, we're back. So we have the difference of two squares. And what expression times itself is equal to tangent squared theta? Well, that's tangent theta. What expression times itself is equal to cotangent squared theta? Well, that's cotangent theta. And of course, you write a plus symbol and a minus symbol. So tangent theta minus cotangent theta cancels out. And you're left with tangent theta plus cotangent theta. And we proved that the left side of the equation is equal to the right side, and that proves the overall equation. Okay, so if you got that right, good job. So now we're going to combine fractions. So let's do some review on adding and subtracting fractions. This is all something that you should know, but if you want to add or subtract fractions, as we mentioned previously, you need a common denominator. So in this case, I would have to multiply both sides of the first fraction by 7 and both sides of the second fraction by 8. And we would get 21 over 56 plus 32 over 56. Again, this is all things that you should know, but in the real world, some students forget these little details. So once you get a common denominator, you can add the numerators, and the denominator doesn't change. It's like 21 bags of gumballs plus 32 bags of gumballs is 53 bags of gumballs. But in this case, instead of gumballs, we're talking about 1/56 of a whole. So in this case, we only have to change the form of one fraction, multiply both sides of the second fraction by 2, and we get 1/6 minus 2/6 is negative 1/6. So in that case, we got a negative fraction. And in this case, we do have to multiply both sides of the fraction. But it's a slightly different situation. So we multiply both sides of the first fraction by 2. And both sides of the second fraction by 3. And how do we know that we did it correctly? Well, because we should have a common denominator after we're done multiplying, and we do. So negative 10 over 18 and 15 over 18. We have a common denominator. We're ready to add them up. So we get 5 over 18. Again, these are things that you should know by now, but you may be a little rusty if you haven't added or subtracted fractions in a while. These things should come back to you pretty quickly. Okay, so let's go on to the next problems. As you can imagine, we're now going to combine fractions by adding or subtracting the fractions. So again, we're going to start with the left side, always the left side, and I'm going to change tangent to sine theta over cosine theta, and cotangent to cosine theta over sine theta. Then I'm going to multiply both sides of the first fraction by sine theta. And I'm going to multiply both sides of the second fraction by cosine theta. So we're going to get sine squared theta. The purple sine and the other sine, they multiply to get sine squared. And on the bottom we have cosine theta times sine theta. And these cosines, if we multiply them, we get cosine squared theta over sine theta times cosine theta. And remember, because of the commutative property of multiplication, these denominators are the same. So even though the order is different, they're the same denominator. So that means that we can add them together. The denominator stays the same. We just add the numerators, and as you can probably tell, sine squared theta plus cosine squared theta is 1. So we used a ratio identity in the first step, 2 ratio identities. Then we used a Pythagorean identity. And we're out of room, but that's okay. We can go up here. We have 1 over cosine theta times sine theta. I'm going to copy that just so we don't have to wonder. And we're trying to get to cosecant theta times secant theta. So we don't really have to show much more work, but I'm going to factor. If you multiply 2 fractions in this form, you'll get 1 over cosine theta times sine theta. So I went backwards. I factored. And the reason I did that is because, look, we're trying to convert to cosecant theta times secant theta. So you can see that that's exactly what we get. The only difference is the order. The order is different, but again, that's not even really necessary to have to change because of the commutative rule of multiplication. So you can see that we got exactly what we need. And I've been forgetting to write my equal signs. Sorry about that. We want to show that we're working on the left side of the equation. So I can put my check mark because we proved it. We proved that the left side of the equation is equal to the right side. And we did that by combining fractions. So let's try another one of these. I'm going to change cosecant to 1 over sine x. And I'm going to write sine x as sine x over 1. So I used a reciprocal identity. I'm then going to multiply both sides of this fraction by sine x in order to get a common denominator. So I'm going to multiply both sides of the fraction by sine x. So we get sine squared x over sine x. And the reason I did that is because now we have a common denominator. So now we have 1 minus sine squared x over sine x. And 1 is the same thing as sine squared x plus cosine squared x. So that was a Pythagorean identity. And I'm going to shrink this stuff a little bit. Or maybe we can just use an arrow. I'm going to use an arrow, so all that stuff becomes, well, the sine squareds cancel out, and we're left with cosine squared x over sine x. Well, now I'm going to factor out a cosine x. So cosine squared is cosine x times cosine x, and you can see up here we're trying to get cotangent x times cosine x, and you can probably see where we're going with this. Cosine x over sine x is a ratio identity. So we get cosine x times cotangent x, and we did it. I'm going to put a check mark. The only difference is the order, but again, that's not really a big deal because of the commutative property of multiplication. Okay, so I want you to take a picture of 25 and 26, and you're going to do 27 on your own. Go ahead and try 27. When you come back, we'll do it together. What you want to do is change this into a fraction somehow by using the ratio identity. Change this into a fraction by changing or using the reciprocal identity. So reciprocal, ratio, combine the two fractions into one. And that's how we're going to prove that this equation is true. Over here we have a very simple expression. It's just one function, so you need to combine all this by changing these into fractions. Try number 27. When you come back, we'll do it together. Okay, we're back, so I'm going to use a reciprocal identity and a ratio identity. So that's ratio and reciprocal. So now I have two fractions. I'm going to multiply the signs, so I get sine squared. And now I have a common denominator, so I don't have to worry about creating a common denominator or changing the fractions so that there's a common denominator. I can just add those fractions up. And 1 is equal to sine squared x plus cosine squared x. The sines cancel out and we're left with cosine squared x over cosine x. And by the way, that was a Pythagorean identity. And cosine squared over cosine, that's just going to be cosine x. And try to remember to write your equal sign so we know that we're only changing the left side of the equation. So we showed that the equation is true. If you got that right, excellent. If you had trouble with that, that's okay. Now you know how to do it. Attempt number 28, and when you come back, we'll do it together. Okay, we're back. So I'm going to change secant to 1 over cosine A. And I'm going to change that cosine A to cosine A over 1. So now we have two fractions. And I'm going to multiply both sides of the fraction at the right by cosine A, and we get 1 over cosine A minus cosine squared A over cosine. Why did I do that? Well, we did it to get a common denominator, and so now we can combine those two fractions into one, and 1 is equal to sine squared A plus cosine squared A. That's a Pythagorean identity. The cosines cancel out and we're left with sine squared A over cosine A. We can then factor out the sine A. Sine squared A is the same thing as sine A times sine A. Then we can use a ratio identity. That becomes tangent A. So we're left with sine A times tangent A. And that's what we're trying to prove. So we're done. So if you look up at the right, we're trying to prove that the left side is equal to sine A times tangent A. We did that. So we can put a big check. If you got that right, excellent. Okay, so now we're going to do problems that are going to use all three. I believe this is a problem that uses all three of the trigonometric identities, all three major types. So we'll see what happens. Cotangent x is cosine x over sine x. So we just used a ratio identity. All right, so that's the first type of trigonometric identity we're going to use. Now, over here we have a cosecant x. I want to convert this expression to cosecant x, but that's just one term. Here we have two terms, so obviously we're going to have to combine the two terms. So I'm going to multiply both sides of the right fraction, or the left fraction that is, times sine x. I guess we'll just use parentheses. And I'm going to multiply both sides of the fraction at the right by 1 minus cosine x. And notice I'm being very careful about where I put the parentheses to avoid confusion. A lot of students would wonder, do I have to use parentheses here? And the answer is absolutely yes, because if you don't, it'll look like you're multiplying sine by cosine, but not by the actual difference. Same thing with here, except it's sine in 1. So now, if we multiply these signs, we get sine squared x over 1 minus cosine x times sine x. I'm just going to leave that factored. And here we can use the distribution property. Cosine x times 1 is cosine x. And cosine x times negative cosine x is negative cosine squared x. So why did I do this? Well, because now we have a common denominator. So we can combine the two. And I'm subtracting these, so you have to be very careful about your signs. I'm going to subtract these. This is a positive cosine x, so it becomes negative cosine x. This is a negative cosine squared x, so it becomes positive cosine squared x. And all of that is over 1 minus cosine x times sine x. So again, all of this, somehow, all of this is going to turn into cosecant x if this equation is really true. So now I'm going to write that cosine squared x next to the sine squared x, just so we can see. You don't have to do that. You can skip that step. And of course, this is a Pythagorean identity. So that all turned into 1. And so now these are going to cancel out. And the sign is still going to be in the denominator. Just because it's isolated now, or it's by itself, doesn't mean that it disappears or that it launches up into the numerator. So I'm going to need a little bit more room. So now we're going to use a reciprocal identity. 1 over sine x obviously is cosecant x, and that's what we're trying to prove. So we did it. So we go all the way back up and we see that that's exactly what we're trying to prove. So that was a very good problem to do, because we used the ratio identity, the Pythagorean identity, and the reciprocal identity. Okay, so now it's time for you to try. Go ahead and attempt number 30. I'm going to go ahead and place this problem up here because it looks like we had plenty of room, more room than I thought. So try number 30, and when you come back, we'll do it together. Okay, we're back. So I'm going to change tangent to sine over cosine. That was a ratio identity. And now I'm going to multiply both sides of the fraction on the left. I'm going to multiply both sides by cosine x. just to keep things balanced, I'll use parentheses on both of these. Visually balanced. And I'm going to multiply both sides of the other fraction by 1 minus sine x. So now we have cosine squared x in the numerator of the first fraction. And I'm going to distribute, so we have sine x minus sine squared x. Alright, and we have a common denominator, that's why we did that. So this negative applies to this whole numerator here. So this is a positive sine x, so it's going to change to negative sine x because we're subtracting that fraction. This is a negative sine squared, so we're going to get positive sine squared x. The signs change because we're subtracting that fraction. Then we have cosine squared x plus sine squared x. So that's a Pythagorean identity. And as you can see, this factor cancels out. So we're left with 1 over cosine x. And if we cheat a little bit and lasso our work, we might be able to fit the final expression. And I forgot to write some equal signs here. We're looking for secant x, and you can see that that's what we get. And so we did it. We proved that the equation is true. Okay, so on to number 31. Looks like we have 4 more of these problems. So let's do 31 together. And you can do 32. Okay, we're going to take the first fraction. And we're going to multiply both sides by tangent A plus 1. Why are we going to do that? Because we have to get a common denominator. It's the only way to get a common denominator. Then we're going to take the second fraction and we're going to multiply both sides by cotangent A plus 1. And when you do that, you have to write parentheses on this blue expression here to avoid confusion. And you have to write parentheses here. And yes, you must do that. It's a requirement, or else the statement is not going to be technically true. It's not going to be correct. So let's double check our work. You want to constantly double check your work as you're moving along here. And I'm going to keep the denominator factored. I'm not really sure what's going to happen to the denominator. We'll figure that out later. we might just keep it in that form, or we might change it to something else. Okay, so we have a common denominator. That's the whole point of all that. So now we're going to add the fractions together, and we get tangent A plus cotangent A plus 1 plus 1 is 2. So we can just leave it as 2. Okay, so I'm not really seeing anything that's going to help us at this point. So let's take the denominator and go ahead and FOIL that. Remember FOIL. You should know FOIL pretty well at this point. So cotangent A times tangent A, that's the first terms. So that's F. So cotangent A times tangent A, that's F of FOIL. And then cotangent A times 1, that's O of FOIL. So that's O. And then I of FOIL is 1 times tangent A. That means inside. O means outside. So we get tangent A. And I'll try purple for that one. And L is the last terms. That's 1 times 1. So it looks pretty bleak at this point. It doesn't look like we're really accomplishing much, but we actually are, because the denominator is going to simplify. We can use a Pythagorean identity, or excuse me, a reciprocal identity. So I'm going to copy this. Whoops, you don't have to show this next step. You can kind of just do it in your head if you want, but we need to show exactly what's going on. So I'm going to rewrite, and by the way, we need a color for the last term there. What color should we use? I'm going to use green. You don't have to use colors. So down here we're going to change cotangent to 1 over tangent A. So that was a reciprocal identity. And 1 over tangent A, focus in on this orange here. 1 over tangent A times tangent A is just 1. And so that's the key that unlocks the mystery of how we're going to do this. We're trying to prove that the whole thing is equal to 1. So 1 plus 1 is 2. And you don't have to show quite so many steps. So we're left with, if we make the bottom look exactly like the top, using the commutative rule of addition, you can see very clearly that this is equal to 1. So we're done. We proved it. We tried to show that that expression was equal to 1. So I want you to try number 32, and when you come back, we'll do it together. Alright, we're back. So we're going to multiply both sides of the first fraction by 1 plus cotangent theta. And maybe just to keep things orderly, I'll just put the parentheses on the 1. Not that I really need to. And the second fraction, we're going to multiply both sides by 1 minus tangent theta. Whoops, I forgot. I need parentheses on this sum here. That's not correct, what I just did there. I must have parentheses, or else that's not correct. I almost violated my own rule. So it's always good to go back and double check everything. It's very easy to forget basic things that you need. Okay, so the first fraction we get 1 plus cotangent theta. And I'm going to use FOIL, so I'm going to go ahead and FOIL this out. So 1 times 1 is 1. 1 times cotangent is cotangent. Negative tangent theta times 1 is negative tangent theta. And negative tangent theta times cotangent theta. That's negative tangent theta, cotangent theta. We can deal with that later, but you can probably remember from the last problem what's going to happen to that last product. So that's the first fraction. And the second fraction we get 1 minus tangent theta over the same thing. 1 plus cotangent theta minus tangent theta minus tangent theta cotangent theta. And the equal sign again signifies that we're staying on the left side of the equation, even though we're having a hard time lining up the equal sign, as you can see. We try to line up the equal sign, but sometimes it's not really practical. Okay, so now we're going to add up the fractions because we have a common denominator, and we get 2 plus cotangent theta minus tangent theta. And what do these equal? You see these here, the yellow? We found that when you multiply those, you get 1. So we have 1 plus cotangent theta minus tangent theta minus tangent theta times 1 over tangent theta, because that's a reciprocal identity. We changed it to 1 over tangent theta. Now again, you don't have to show quite this many steps. You can kind of skip a few things. But when you multiply these, we get 1. So we have minus 1. The 1's cancel out, and we're left with 2 plus cotangent theta minus tangent theta over cotangent theta minus tangent theta. So there you go. We proved it. Now, a lot of students would say, wait a second, can't we just cancel these out? Let's cancel these and cancel these. Well, no, we cannot do that because the 2 is here, and what that means is that cotangent theta minus tangent theta is not a factor of the numerator. It is a factor, you could say, of the denominator, but not of the numerator. So that's a good idea, but it doesn't work. But we did prove that equation is true. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and screenshot number 2 and number 3, number 4, number 5, and number 6, number 7, and number 8, and number 9. And number 10. But don't go before we get your homework. Here's the homework. Screenshot number 1. And that's really the only screenshot, but don't go before you get the answers. Remember, it's not enough to attempt the homework. You need to do it correctly. So here's screenshot number 1 of the answers, and screenshot number 2. And be aware, screenshot number 3, be aware that there's more than one way to prove these equations. So if you do it in a slightly different way, that doesn't mean that it's necessarily wrong. And here's the last screenshot. So get that homework done completely, correctly, neatly, and keep it in order in your binder. Remember, if you don't do the homework, it's a 100% guarantee that you're going to learn absolutely nothing in this entire course. So get that homework done, and I'll see you in the next class.